In 2017, a company lost the personal data of 148 million people. The break-in itself was boring, a known bug in a library they hadn't updated. But the reason nobody noticed for 76 days is the part that should keep you up at night. The alarm system watching their traffic had been dead for 19 months because a certificate had quietly expired. The day they finally renewed it, they found the intruders. That same day. Welcome back. Last time we built the entire road out into the world. Your code left the locked room, moved onto a machine that never sleeps, put on a name people can type, wrapped its conversations in a sealed envelope, and learned to survive a crowd. So you're finished, right? 2 things left. And both of them are the kind that end companies. First, you still have to take money, log people in, and send mail, and you should not build any of those yourself. Second, your front door is currently standing wide open. Today, we close both. Let's start with the valley beginners fall into every single time. I'll just build it all myself. Payments, login, email. It sounds impressive when you say it out loud. Build payments yourself and the card industry's security standard chains you up for months. Build login yourself and you personally own the liability for every password leak, forever. Run your own mail server and every letter you send marches directly into the spam folder. In all 3 cases, I can do it and I should do it are entirely different countries. So you borrow. You reach a hand through a counter somebody else built, an API, and shake on it. And I want you to appreciate how recent this ease actually is. In the year 2000, Salesforce became roughly the first company to sell an API as part of a product, and it was a heavy, finicky thing that shipped with a PDF manual over 400 pages long. Renting someone else's system could genuinely take longer than building your own from scratch. 3 things you'll meet at that counter. The API key is your pass and ID badge. Attach it to every request, and the shop knows you're a paying customer. The SDK is a toolbox the shop prepacks so the whole fussy procedure collapses into a single line of function. Raw ingredients versus the meal kit. For a vibe coder, obviously the meal kit. The third one confuses everybody at first, the webhook. Normally your server is the one asking the other side, "Done yet?" But some jobs have genuinely unpredictable timing. A payment approval might land in 1 second, or take 30, because a bank somewhere is thinking about it. So, option 1 is polling. You phone every few seconds. Done? 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 Tiring, wasteful, and slightly undignified. Option 2 is the webhook. You leave your number and say, "Call me when it's finished." Then the instant it happens, they phone your server first. Payment complete. Anything you can't predict the timing of, payment confirmed, shipping status changed, subscription renewed, runs on webhooks. Don't wait. Get notified. And this entire culture of chopping work up and farming it out by API was allegedly forced into existence inside one company by decree. Around 2002, Jeff Bezos reportedly handed Amazon a mandate. Every team exposes its data and functionality only through service interfaces. All team-to-team communication goes through those interfaces. Peeking directly into another team's database or sneaking around through a back door is flatly forbidden. And the last line is the one everybody quotes. Anyone who doesn't do this will be fired. Now, the way this story got famous is my favorite detail. A former engineer, Steve Yegg, wrote it up in a long retrospective post in 2011, which he meant to share internally only and accidentally published to the entire internet. A post about the dangers of bypassing the proper interface, released to the world by clicking the wrong button. That mandate is also, incidentally, how Amazon accidentally laid the foundation of AWS. Now payments, the junction to handle most carefully in this entire book. Bottom line first, your server should never directly touch the card number. Ever, if you can possibly help it. The card industry has a security standard called PCI DSS, and the moment you receive, process, or store card data, the list of requirements you must personally satisfy balloons. And if that information leaks, the liability is beyond imagining. This is not a load a vibe coder should carry. Honestly, most real companies don't want to carry it either. So Stripe's idea was clever. We'll take the card data. You don't touch it. The card goes straight from the customer to the payment company, and your server gets back only a safe token.
Picture it this way.
A customer walks in holding a wad of cash. You never touch the cash. They feed it into the deposit machine at the counter themselves and hand you only a receipt number. All you ever do is ask, "Was that confirmed?" You can't leak information you never held in the first place. Then here's the actual flow. Card goes straight to the payment company. They hand your server a token. Your server requests approval using that token. And finally, they notify your server by webhook that it's confirmed. You mark the order complete off that webhook. Never off the screen. The screen said success, sure, and then the network dropped, or the user closed the window, or it got declined at the last second. Don't trust the screen. Trust the server. Stripe started at two brothers' kitchen table. Patrick and John Collison, from Limerick, Ireland, had already run internet businesses, and they felt it in their bones that the single hardest part of the whole endeavor turned out to be figuring out how to take the customer's money. And the project, begun in the fall of 2009, was not originally called the tidy, professional Stripe. It was called /dev/payments, mimicking a Unix file path, a name that flatly announced exactly who they were building for, and that would have meant absolutely nothing to a single human being in finance. Patrick, by the way, won Ireland's National Young Scientist exhibition at 16 for a programming language he built himself. That's where the instinct for a developer-friendly API comes from. It was there before the company was. Patrick dropped out of MIT. John dropped out of Harvard. Two elite universities abandoned side by side for an infrastructure company that took money for other people. In November 2016, they became the world's youngest self-made billionaires. John was 26 at the time. And how they landed their first customers is famous enough to be in the textbooks. When someone said, "Sure, I'll give Stripe a try," the brothers didn't email over some instructions. They said, "Hand me your laptop," and installed it on the spot, right there in front of them. Y Combinator entered this into its permanent vocabulary as the Collison installation, and Paul Graham used it as the example in his essay, "Do Things That Don't Scale." Completely impossible with 1 million customers. Absolutely perfect for your first 100. Now here's the real lesson, and it's the thesis of this whole lecture. Stripe's famous pitch was that 7 lines of code gets you payments. But Stripe did not eliminate the complexity. It absorbed it. Behind those elegant 7 lines sit fraud detection, regulatory compliance, relationships with banks, risk modeling, settlement infrastructure, all of it whole and intact. It didn't vanish. Somebody bears that weight. It's simply not you. Same story with login. Sign in with Google isn't a convenience feature. It's a clever structure for offloading risk. Build login yourself and you must store passwords, and stored passwords are a minefield where one leak is game over. OAuth hands that job to Google, who is measurably better at it, and you receive back only a token. It's not the hotel master key. It's a key card that opens room 203 and nothing else. And notice this was a movement, not one clever company. Twilio, founded in 2008, took phone calls and text messages, a domain where you previously had to negotiate directly with telecom carriers, and abstracted the whole thing into a single line of API. Co-founder Jeff Lawson published all the pricing and all the documentation openly on the website, specifically so a developer working at 2 a.m. never had to wait for a sales representative to call them back. The title of the book he later wrote captures the entire philosophy in 3 words: ask your developer. Payments, authentication, messaging. The pattern was identical every time. Find the specialist in that field and delegate to them by API. Which brings us to the last junction: actually talking to humans. Welcome emails, password resets, order confirmations, shipping alerts. These are called transactional messages, functional notifications, not advertising. And the same trap waits here. Mail. At least, I'll just send from my own server. Please don't. The mail world runs entirely on reputation, and a letter from a brand new server nobody has ever heard of gets suspected first by the receiving system. Which means your password reset email lands in spam, and your user is simply locked out of their own account forever. So you hand the envelope to a courier with an established reputation. And notice how this stitches back to last lecture. The sender trust settings that make delivery actually work, SPF and DKIM, are configured as TXT records on the domain you set up 2 chapters ago. Domain configuration and mail delivery turn out to be the same wire.
Right.
Money handled, login handled, mail handled. Now the last ridge, the one people skip, and the one that ends companies. Nobody leaves their front door wide open when they head out for the day. A startling number of people ship code exactly that way. And bottom line first, an AI is excellent at writing code that works. It does not write secure code by default. The gap between those 2 sentences is the entire point of this half of the lecture. Tell a carpenter, build me a room and you get walls, a floor, a ceiling. Beautiful. But unless you also said with a lock on the door, you may well get a door with no lock. That's not laziness. Your request didn't mention a lock. So, let's kill the most dangerous sentence in vibe coding right now. Let me get it working first, security later. Security isn't a later. It's a from the moment you ask. And let's kill the second most dangerous one. My service is small, nobody's heard of it, hackers won't care. Exactly backwards. What's coming for you isn't a person who has evaluated whether you're interesting. It's an automated scanner sweeping entire ranges of internet addresses, rattling every doorknob it finds, completely indifferent to whether you're famous. Being small doesn't make you safe. It usually just means your locks are flimsier, which makes you the easier target, not the ignored one. Checkpoint 1. Your secrets. API keys, database passwords, access tokens. The keys that prove you're you. Bake one directly into your code and upload that code to a public repository, and that is precisely equivalent to taping your house key to your front door with a note reading, "This is the key to my house." Except it isn't a passerby in the alley who finds it. Bots sweep for key patterns around the clock, and getting harvested within minutes of upload is not rare, it's normal. And if that key belongs to a service that bills you, like cloud infrastructure or an AI API, then somebody goes wild burning resources in your name, and a spectacular invoice lands on you days later. The fix: pull the values into a separate environment file, and put that file into your ignore list, so it can never be uploaded. Your code keeps the instruction to read the value, never the value itself. And here's the part people get wrong under pressure. If it is already leaked, deleting it is not enough. The bot may have taken it minutes ago, and your commit history may still hold that value perfectly intact even after you delete the line. The only real fix is rotation. Retire the old key immediately on that service and issue a new one. A leaked key cannot be recalled, so you change the lock itself. Also, please retire this belief. It's a private repository, so baking the key in is fine. Private repos leak. Collaborators get added. Permissions get misconfigured. Repos flip public later. One enormous breach that spilled the data of 57 million people started from exactly that. A hard-coded key sitting in a private repository. Checkpoint 2. Everything arriving from outside is a potential weapon. Most of your users are lovely people. You still handle every single input on the assumption that it's an attack, because security is designed around the malice of the few, not the goodwill of the many. Here's SQL injection with a fresh analogy. At a restaurant, you write the dish name on an order slip and pass it to the kitchen. A normal customer writes kimchi stew. A malicious one writes, in the dish name field, kimchi stew. And the chef will open the safe and bring out all the cash. If the kitchen reads that entire slip as instructions, you're finished. That's injection, a command wearing a disguise, sitting in a data field. And the defense is to nail down in advance that this field is data, period, no matter what letters somebody wrote in it. SQL injection has an exact birthday, and it's a good one. December 25th, 1998. Christmas Day. A hacker publicly demonstrated in a hacker magazine that with basic coding skill you could staple unauthorized commands onto a normal database command and pull sensitive information straight out. Somebody spent their Christmas doing that, and 25 years later, we are still cleaning up after it. But what actually made injection world famous wasn't a security paper. It was a single comic panel. A 2007 XKCD strip where a school phones a mother to ask whether her son is really named. And I'm going to read the punctuation out loud here. Robert, close paren, semicolon, drop table students. And she answers, oh yes. We call him Little Bobby Tables. That joke is now the de facto standard reference for explaining injection to anyone. One good analogy travels farther than 100 warnings. The second classic, XSS, targets not your database, but another user's screen. Someone posts a comment that isn't ordinary text, it's a malicious script. And if your site prints that comment untouched onto the next visitor's screen, the script runs inside their browser. One person sets the trap, and your site politely delivers it to everyone on their behalf. The defense is output escaping, neutralizing script symbols so they render as visible characters instead of running as code. Most modern frameworks do this by default, and the trap is the convenience feature that deliberately switches the protection off. And the name, it really should be CSS, for cross-site scripting. But CSS was already taken by the style sheets from Region 1. So they shortened cross to X out of pure naming desperation, and we have called it XSS ever since. Even the vocabulary of security has web history fossilized inside it. Checkpoint 3. Once somebody is inside, how far can they go? 2 words that sound identical and aren't. Authentication asks, who are you? That's login. Authorization asks, are you allowed to see this? And here is where nearly everyone slips. They guard authentication carefully and skip authorization entirely. Logged in. Good enough. Wave them through. So user A views their own order at an address ending in 1001. Then it changes that number to 1002, and a complete stranger's order history is sitting right there in front of them. The login was entirely legitimate. Nobody ever checked whether that order belonged to them. Authentication is the badge that gets you into the lobby. Authorization decides which floors that badge opens. And if the badge opens every door in the building, that isn't security. That's an automatic door. So where does the wall actually go? The decisive principle. Hiding something on the screen is not security. Making the delete button invisible is user convenience, nothing more. Anyone can fire that same request straight at your server with a tool, and it will run anyway. The real lock goes at the server and at the database layer, which is why row-level security is so reassuring for a vibe coder. It enforces, row by row inside the database itself, the rule that you only ever see your own rows. So no matter who asks, through whatever path, the database itself refuses to hand it over. That kills the 1001 to 1002 problem at the root, where the data actually lives. One caution, and it's the whole reason the checklist exists, a protection that powerful still only works if you remember to turn it on. 2 people and 1 cautionary tale, and then we're done. On September 9th, 2001, Mark Curphey launched OWASP with no org chart, no funding, and no staff. Just one announcement to a mailing list and a registered domain name. It started as a security handbook and a deliberately vulnerable practice app and grew into the top 10, the industry's standard list of the most critical risks in web security. The reason you can say to an AI, review this from an OWASP angle, and have that mean something concrete is that Curphey gave scattered security knowledge a common vocabulary. And the twist, Around 2022, he publicly criticized the very organization he founded for losing its relevance. The mapmaker knew better than anyone that you aren't finished when the map is drawn. When the terrain shifts, you redraw it. April 2014. Neel Mehta of Google's security team had a hunch that more danger was hiding in OpenSSL, the library that encrypts the internet's communications. So he audited it line by line and found a critical bug that nobody had seen in years. At disclosure, roughly 17% of secure web servers holding trusted certificates were vulnerable. About 500,000 machines. Half the internet had been standing there with a window wide open the whole time. Then, days after he reported it, a security firm in Finland independently found the exact same bug. Invisible for years, then spotted twice in 1 week. And what carried it to the general public was the naming. Normally, a vulnerability gets a dry serial number and dies in obscurity. They gave this one a memorable name, Heartbleed, a bleeding heart logo, and its own website. And with that, an ordinary bug made the evening news. Security travels the same way everything else does, through an analogy and a name. And now the cautionary tale from the top of this lecture. On October 3rd, 2017, Equifax CEO Richard Smith testified before the U.S. Congress that as CEO, he was ultimately responsible for what happened on his watch, and that to every single person affected, he was deeply sorry. He had already resigned a week earlier. The break-in began at an unpatched library, a known vulnerability in a component they'd simply left sitting there. That's the dependency item on every checklist ever written. But the reason data bled out for 76 days with nobody noticing lay somewhere else entirely. The security appliance monitoring their traffic had been effectively dead for 19 months because a certificate expired. At the time, that company had let hundreds of certificates expire. And the moment they renewed that one, they discovered the intrusion the same day. A protection only protects while it's switched on and alive. That's not a slogan on a poster. That's 148 million people. So here is the checklist you skim every single time you go out. You don't memorize it. You read it. Are your secrets separated out into an environment file and excluded from the repository? Have you ever uploaded a key by accident in the past? And if you even suspect it, did you rotate it? Does the site load over HTTPS? Are you using parameter binding or an ORM instead of assembling database commands as raw strings? Did you leave the framework's default output escaping switched on? Then, are there any see other people's stuff holes? And did you actually turn on permissions at the database layer? Are your dependencies updated? Or is there a known vulnerability sitting in something you installed a year ago? Do your error messages avoid printing file paths and database structure to strangers? And did you change the default admin password? That's it. That's the whole door. And now the practical half, how you actually put an AI on this. As I said at the start, it won't unless you ask. Flip that around and the good news appears. Ask. And it does this genuinely well. The key isn't a fuzzy, please make it secure. It's pointing precisely at what to check, by which standard. Review this from an OWASP angle, sorted by severity. Then show me the fixes. Add injection and XSS defenses to this input handler. Validate on the way in, escape on the way out. Add an authorization check, so a logged-in user can only reach their own data. Sweep this repository for exposed secrets. And one more, because an AI saying security handled is not itself security. Explain line by line which vulnerability you blocked and by what method. The person who knows how to point also knows how to verify. So, where are we standing? 2 lectures ago, your code was trapped in a locked room, pointing at a mirror, visible only to you. Now it lives on a machine that never sleeps. It wears a name people can type, and its conversations travel sealed. It survives a crowd. It takes money without ever touching a card. It logs people in without ever storing a password. It sends mail that actually arrives. And its door is locked, Its inputs are inspected, and its permissions are enforced at the deepest layer, where the data really lives. Region 4 is complete. That's a real service. Let's tie it together. 2 gates today. Gate 4. You don't build it alone. Payments go to payment specialists, and your server never touches a card number because PCI DSS is a weight somebody else is willing to carry. Login goes to Google or Apple because information you don't store cannot leak. Mail goes to couriers who spent years building the sender reputation you don't have. And the pattern is always the same 3 pieces. A key that proves who you are, a toolbox that collapses the procedure into one line, and a webhook so you get notified instead of waiting. And the deeper lesson from Stripe: nobody eliminated the complexity. They absorbed it. Fraud detection, compliance, banks, settlement, all still there, all still heavy. It's just not on your back anymore. Gate 5. The locks in the order you set them. Separate the secrets and rotate immediately if you even suspect a leak. Validate what comes in and escape what goes out, so a command can't hide inside a data field and a script can't ride your site onto someone else's screen. Build the wall of permissions at the server and the database, never on the screen, because hiding and locking are entirely different acts. And run the checklist before you ship. The one sentence to carry out of here: security isn't a later, it's a from the moment you ask, and unless you ask, an AI won't do it. Not because it's careless, because it builds what you described and you didn't mention a lock. Everything in these 2 lectures comes from Region 4 of a book called the AI Development Atlas. It's built on one idea. In the age of AI, the person who commands the tool isn't the one who memorized the most syntax, it's the one who knows the terrain, who can point at the map and say precisely, the problem is right here. 10 regions, from the front end all the way to AI transformation, each drawn as terrain you can actually walk. If this road made sense to you, the full atlas is available now, and the link is in the description below. Next time the ground changes completely. We leave the land of the web behind, everything we've walked for 5 lectures, and step onto a new continent, where machines stop following instructions and start learning on their own. Region 5, Machine Learning and Deep Learning. If this was useful, subscribe and I'll see you on the next trail. DK Corporation, know the terrain. Command the tools.